Good morning, everyone. Today I'll be presenting my MS research work, which is titled as TRNG based on multiple entropy sources using CTDSM. Okay, so this is the outline of the presentation. First, I'll do the brief introduction about TRNG, and then we'll go to literature survey, and then we'll discuss about our motivation around using CTDSM for TRNG. CTDSM that we exploited to design TRNG. And at last we'll discuss about our proposed design. So two random number generators are supposed to generate independent non-reproducible outcome, and so for that entropy should be maximum, and it's basically imitating a fair coin toss. And it is very different from pseudo random number generator that is usually used in many computers. So that use algorithm, but in two random number generators, we use real noise source and translate it into random outcomes, random numbers. So in two random number generators, it relies on entropy sources present in the circuit, the random processes happening in the circuit for the randomness, and it's very critical for hardware security and cryptographic algorithm applications. And the TRNGs are validated using a NIST test suite that has like battery of tests of 15 tests, and it judges a quality of TRNG and validates whether it is suitable for the desired application or not. So one of the major challenges in TRNG design is biasness in the output. So for that, we have to rely on post-processing. So these are the commonly used post-processing techniques. One is XOR-based post-processing. So in XOR-based processing is basically if we have two random variables with bias B1 and B2, XOR of those two binary random variable bias reduced by the product of those two biases. So it doesn't completely eliminate the bias, but it reduces the bias. And there is one another way is von Neumann corrector. So in von Neumann corrector, the bias is completely removed, but the problem is that the maximum throughput we can achieve is 1/4 of the throughput of the input random variable. So there are also many other techniques, compression based techniques based on error correcting codes. And one more challenge in designing two random number generators is correlation among the samples. So as we know that for a perfectly independent, for a zero correlation binary random variable, its power spectral density should look completely white. But if we have any kind of correlation, the power spectral density will have a colored outcome. So what we need is zero unity autocorrelation function at zero lag and zero autocorrelation function elsewhere for our TRNG design. And basically, autocorrelation and Shannon entropy are two basic metrics used to assess the quality of the two random number generator. But these two have some limitations. Shannon entropy misses out on local patterns, and it looks on overall entropy. It's not the perfect measure of entropy. And whereas autocorrelation also ignores like higher order dependence. So we have to resort to NIST test suite that is standardized for TRNG design. So it has like battery of tests, 15 tests. So only if you pass all the tests, then only you can say that you have a truly random output. So now we'll look some existing work on TRNG. So this is a broadly classified class of TRNG based on the device noises such as random telegraph noise, soft breakdown noise of MOS. So in the highly scaled transistor, the 1/f noise after technology scaling becomes it becomes flat for some spectrum, and but for very low frequency, up to very low frequency, so that can be used for to extract randomness out of it. The shortcoming in these kind of TRNGs are the throughput is very low, and one okay. So another class is based on coupled ring oscillator. In this, multiple ring oscillators are used, and multiple ring oscillators are used to extract jitter event from each other, and the extra randomness is added by XORing all of them at the same time. So this uncertainty helps us to generate a good quality random sequence. And these kind of coupled ring oscillator based TRNGs are designed using FPGAs. But the issue in these kind of ring oscillator based TRNGs are that it might suffer from frequency blocking problems. So like multiple multiple ring oscillator might become correlated in the long run. So so for that, in one of the papers, they used programmable delay line, and they were providing seed through A1, A2, A3, A4. And one major thing in this kind of true random number generator is they required heavy post processing to meet the NIST standard. So based on ring oscillator only, there is one more class is chaotic ring oscillator based TRNG. In this, they basically amplify the jitter. So basically, they use two ring oscillator and they do non-linear coupling. So one of the method of non-linear coupling is shown here using transmission gate. So using that manifest into that non-linear coupling manifest into the jitter out of this oscillator, jitter into this oscillator output, and so that amplified jitter is sampled using a very fast clock, which is the clock frequency of that is comparable to the standard deviation of the jitter. So through that they generate random number sequence. So this is one another class of TRNG based on metastability. So in this they use latch cross coupled inverter. So and they bias it in the metastable region, and but in this in practical scenario there will be some kind of mismatches and there will be some kind of imbalances. So they use a very sophisticated feedback mechanism to compensate, to force or find correcting those mismatches to be able to perfectly bias it into the metastable region, and then through that they generated random number sequence. But the drawback is the whole system is very big and the feedback mechanism is very complex. Yes. And this is one more class of TRNG based on the ADC. So on the left side, we have delta sigma based TRNG. They used in one paper they used delta sigma modulator, and another they used SAR ADC. So they are claiming that they can be used simultaneously as ADC as well as TRNG. But the drawback in this is the randomness in the output is heavily dependent on the input. So only if the input signal is busy enough, they are relying on the quantization noise and other noise. So only if the input signal is busy enough, then only the output is random, and the randomness can be altered if the input signal is not as desired. So this is our motivation behind using continuous time delta sigma modulator. In this, there are multiple uncorrelated noise sources which can be intermixed that affects this noise floor. So such as like for a reference input we can use thermal noise, already quantization noise is there, and phase noise in both ADC and DAC, and metastability can also be induced in the ADC. So all these have different distribution, but they will converge to Gaussian distribution at the point yt, and that can be like sampled to get the random sequence. That was our motivation, to use multiple uncorrelated noise sources for TRNG design. So this was our setup. We wanted to use like CTDSM to extract entropy, and the best way to extract randomness from CTDSM is through sampling the LSB of the CTDSM, because in LSB captures the smallest change and it is least affected by the circuit offset. So for generating a unbiased random bit stream, which is IID, samples of multiple instances of CTDSM are XORed together. So and LSB are selected because even if some bias is present, the whole distribution of noise will move up and down around the threshold, but it won't change the distribution itself. So the actual randomness will be intact. So we'll discuss a little bit about STF and NTF of CTDSM. So this is the block level model of CTDSM, and that is rearranged in the figure below. And as we can see, the NTF and STF are high pass and low pass transfer functions respectively. So we did, based on the transfer function and the noise models, we did the noise analysis in first order first order single bit CTDSM topology and other topologies also. So we'll just go through quickly around about all this. So we added thermal noise at the input. So thermal noise will directly pass through a signal transfer function, and its variance can be easily calculated using the equation given. So, and this is the quantization noise which is added at the ADC's input, and it gets shaped through the noise transfer function. And similarly, we know the PSD of the quantization noise, so its variance can also be easily calculated. And for thermal noise, aliasing will, since it is wideband noise, so aliasing will also happen. So we considered the effect of aliasing also, and we calculated the variance across all the alias frequency that can make a contribution. So for that the result is given. We can see that since CTDSM has excellent alias rejection, and STF suppresses as we move along the high frequency. So the contribution becomes nil as we go at the high frequency. Okay, so now we'll look at the clock jitter effect on CTDSM. So clock jitter are assumed to be like Gaussian distributed and white. So in CTDSM, jitter in the clock of ADC and DAC both can affect the noise floor of it. So through the jittering clock of ADC, an additional error sequence gets induced that is added at the shown point, that is EADCN, and through the effect of jittering clock DAC, additional error sequence induced, that is EDACN as shown. So, and they will accordingly see the respective transfer functions. So we'll just quickly look at the modeling, how we analyze the noise variance in case of clock ADC. So to actually estimate the error value, we can take the difference between ADC sampling through ideal clock and jittered clock. So through Taylor series, we can write it like delta Tn into dy by dt at each sampling frequency. But and that error is estimated using just the slope multiplying y of n ts minus y of n minus 1 ts by ts, that is the slope multiplied by the random jitter. And this, so through that we get the error sequence for each at each instances, and that yn minus y of n minus 1 upon ts, we know that at the input of ADC, the transfer function is input times STF, input time STF minus 1 plus quantization noise time NTF. So through that equation, yn minus 1 is modeled, that is shown in block diagram, and based on the transfer function is seen from those points, the overall variance is calculated. And so finally, based on the transfer function, we can estimate the variance. Add variance of noise added at the input of the ADC, and that will eventually see NTF again. So that will again shaped out like quantization noise. So for that we can easily calculate the noise variance. And similar thing is done for jitter in DAC also. So for suppose we are getting DAC input code as shown in first block. So for in case of suppose we have energy DAC, so in case of energy DAC we will get pulses like that. So equivalent error due to jitter can be shown as EDAC. So these EDAC can be modeled as a impulses having the area of value of the respective error, and so that is given by delta Tn, that is random variable, multiplied by Vn minus 1 at each instances of the sample, and that is again that occurs at the output of that. So that is referred to the input of the DAC, so that it can be easily modeled. So basically it's just divided by Ts. So each impulse is spread across the pulse area, so that it can be easily written. So finally we get this EDACN sequence, model of EDACN, which are used to calculate the variance of jitter due to jittering clock DAC. And again, this Vn minus 1 is modeled again as discussed earlier, and since it is occurring directly at the Vn output of the CTDSM, mean square value is calculated. So that is shown. Also, due to jittering clock of DAC in CTDSM, it affects differently based on the pulse shape of the DAC. So for NRG DAC, the error model is different. For return to zero DAC, for switch capacitor resistor DAC, the model is different as shown here. One more thing is in CTDSM alias rejection, it has inherently excellent alias rejection. But if we use switch capacitor resistor CTDSM, DAC in our CTDSM, the alias rejection gets severely compromised. So high frequency noise around the alias bands gets folded back. So basically STF gets degraded by the practical value of the OTA used in the integrator. So that is shown here. So we intended to one more thing I want to discuss here. We can see in these modeling, return to zero DAC is more severely affected due to clock jitter, and then followed by NRG DAC, and SCR DAC is least affected. We can see that because it quickly dies down. But through SCR DAC it can compromise the alias rejection, and through RG DAC we can have like very high jitter sensitivity. So we use weighted combination of return to zero DAC and SCR DAC in our design, so that we can get both alias rejection as well as high jitter sensitivity. Also, metastability can be induced in the comparator. So all the comparators used in our flash ADC. So if the samples at YT is fallen near the threshold value of those comparators, it can go into metastability, and it gets randomly resolved based on the virtue of event at those nodes. And so we can play with the time constant of the comparator used. We can use long channel transistor as well as and we can load the nodes also to high value of capacitance to reduce the time constant, so that the likelihood of it going to metastability will be increased. So there are two effects of metastability in delta sigma modulator. One, if the samples of input is Gaussian random process, and if the samples of YT falls near the threshold, it might get randomly resolved, and it can appear as a random value at the output. And the other effect is based on the samples, there will be a signal dependent delay, like to resolve. If the sample is very close to threshold, the clock to Q delay, if it is stuck in metastability, the clock to Q delay can be modeled as a Poisson's process. But if it is, so the delay value is a random variable here. So that will manifest similar to jitter in the dial, and that will also modulate the phase of the feedback. So accordingly, this E meta n, this error sequence is only modeling the signal dependent delay part of it. The other random resolution due to sample falling near the threshold is like difficult to capture. So this error model is only capturing the other part. So we have all the error models. So based on those error models, we calculated the noise variance for which two cases are shown here. So in first order 1-bit case, we can see that it is like heavily dominated by quantization noise and the effect of other noise sources. Though we ensure that we inject maximum possible noise from all the sources, is like very minimum as compared to quantization noise. And for high, so to reduce quantization noise, we move to higher resolution. So here we can see that more comparable distribution. So we opted for multi-bit design choice in case of delta sigma modulator. And prior to that, during this analysis, we also tried for single bit first order modulator. So that is evident from our analysis that it doesn't generate random sequence, and it is shown here. Though we added ideal buffers and all the ideal elements to maximize the noise injection from all the points, the PSD is not looking flat, and also we can see that non-zero correlation at non-zero lag value, that is not desired. So we designed this 4-bit CTDSM based TRNG. We used through R1 and R2 we generated thermal noise, and its variance is boosted using a high gain OTA, and it is injected at both the nodes of the integrator. Also, this CRO is chaotic ring oscillators. So these chaotic ring oscillators are used to generate jittery clocks. So we are able to achieve around 20% jitter to period ratio through it, and we designed flash ADC and switch capacitor return to zero lag to get advantage of both aliasing as well as high jitter sensitivity. So, and finally the LSB output was sampled for the random sequence. So we can first see the aspect of this thermal noise injection through high gain OTA into integrator. So both nodes here, high gain OTA will be imbalanced through the input impedance of the integrator. Both nodes will see different impedances. So suppose we will see the differential thermal noise as alpha times V noise by 2 and minus beta times V noise by 2. But both will see the different transfer function. The positive terminal will see 1 plus 1 by S transfer function. Negative terminal will see simply 1 by S. So accordingly, we will get this output at the output of the integrator, that is Vn by 2 alpha by S plus beta by S. So though some attenuation, we will get the noise at the integrator's output. And extra alpha Vn by 2 noise is also added at the output of the integrator, which aids in increasing the randomness. Also, there is one more problem here. The time constant of integrator is also reduced through this setup. So that can lead to long chain of ones and zeros. So that we solve through post processing. Okay, so this is our quantizer setup, that is 4-bit flash ADC and 4-bit switch capacitor RG DAC. So we use high time constant comparator for flash ADC, and for switch capacitor RG DAC, since the mean and standard deviation of the random process seen at the input of the quantizer is not covering the entire dynamic range of the quantizer, so we adjusted it so that the resolution will be better. So we used for flash ADC it is easy to like bias, but for DAC we use always on and always off DAC unit DAC elements, and through that we can move the window, so the average value will change, and bias, a little bit bias can also be adjusted by you selecting the MMM value. Okay. And for clock generation, we use chaotic ring oscillator. We directly took it from one of our references, and through that we were able to generate jitter to period ratio of approximately 20%. And this is the phase plot just to show that it is going into chaotic regime. So it has unpredictable trajectories. So that can show that it has become a chaotic system. So finally, we tested our output sample through our TRNG. So we used 3 different instances of CTDSM and XOR of those instances. So we can see the autocorrelation factor is very close to 0 at all the lag value in all those 3 instances. But there are some micro correlations, but that is also mitigated after the post processing, and we get like very close to tightly packed to 0 autocorrelation value at all the lag values. And that is a zoom view of the autocorrelation factor. So we can see that it has window of plus minus 5 milli, and unity of ACF at 1 value. And this is the FFT plot of the data we obtained, and we can see it is appearing white. And finally, we tested for NIST test, and it passes all the randomness tests. So our conclusion is we did qualitative and quantitative analysis of all the noise sources, and we studied their modeling, and through those models we analyzed the variance, and we gave a theoretical justification of our design choices. And we use multi-bit quantizer to balance all the noise in our CTDSM, and we use circuit design. We implemented circuit design to generate both weighted combination of RG DAC and switch capacitor DAC, and we use chaotic ring oscillator for ADCM, the clocking ADCM DAC. And these are the future works that can be operated in this project. So it is yet to be verified across the PVT, and also some design optimization can be done for power consumption, and we also have to analyze the environmental impact like supply noise attack or any electromagnetic effect on entropy on due to any electromagnetic interference, and we can also like opt for like better post processing. Thank you.